Right. Right. So this is module 11, embedded systems, IoT, and cloud computing. So these are three different topics actually. What is it? Right. All good. Yes. Embedded systems, IoT, and cloud computing. So three different topics. Basically, these are one of major topics that you need to learn in three separate streams. But under these fundamentals, what we are doing is we are giving very high level overview on these three topics. So last week we was focused on networking and internet, how this internet works and different kinds of networking components are connected together to communicate with each other. So under this module, we are mainly focusing on embedded systems, basically the systems that uses internet. Right? So embedded systems are very detailed or very comprehensive uh, hardware products, basically, because the software is embedded into this hardware component. Nowadays, these embedded systems are minimizing their work and more towards IoT, Internet of Things, are coming into the context. On the other hand, cloud computing is one of very important, very powerful. You should must, because without cloud computing, you can't learn in work in industry. We have different kinds of cloud service providers, different infrastructures, and different mechanisms, different vendors with different purposes under this cloud computing we can find. So basically, the module objectives for this today is on completion of this module, students should be able to describe what embedded systems are. Basically, you need to describe what are these embedded systems and the key design considerations and principles of operations. You know, once it comes to the design considerations, we have to focus on different design aspects, and furthermore, how these operations are work, principles of operations, how it was worked in here and there. List the most common types and applications of embedded systems. So you need to focus on listing down the most common types and their applications of embedded systems. Under these embedded systems are much more towards for the discussion related to the Internet of Things. Describe what IoT is, its impact and usage considerations, and explanation how embedded systems from a crucial element of IoT. Now, basically, you should be able to understand or describe in a free format what is an IoT device and what are the contexts related to this IoT and its impact, usage consideration, and explanation how embedded systems from a crucial element. Now, once it comes to the, I told it, the embedded systems that we are focusing on is much towards IoT. So basically, what we are mainly learning in our generation, what we are learning basically IoT instead of embedded systems, because we keep these embedded systems for electrical and electronic engineers. They mainly focusing on this product. Describe the evolution of cloud computing. So we'll see what is this cloud computing, how it works, and so on and so forth. List the levels of cloud computing services and explain their principles of operation. Basically, how it works. Right? So different kinds of cloud computing services and principles of operation, how these are working. some of infrastructural components, some of usage or the vendors and different kinds of operations that we have. We'll see what are these components that we need to learn in here and there. Some of categories of computers which was learned previously. Embedded computers. Basically, embedded computers are integrated into large device or system to monitor and control. Basically, it provides an opportunity for us to integrate large devices like big applications, like kind of monitoring and working. But nowadays, we don't have these embedded computers, paging devices. Sometimes you have heard time back we don't have SMS services. Instead of that, we have paging, a device, a specific device. What this device is doing, there is a person who generates the signals or send a message. Then the person who received that, like kind of a mobile, but a text will appear in there. It's like text is going on that screen. So it's a nice implementation at that time. But nowadays it's like a piece of like nothing. No need, used for specific purpose rather than general processing. As an example, some of phones, cars, and so on and so forth. One of nice example is the paging devices, pages. So it's a kind of a mobile, and we can, like, not everyone, the people who are working like as a senders, they can send the message to the receivers. It's like a mobile device, but it's just showing what of some of information that we want. And basically these devices are very easy to handle because the functionalities are very limited. Most probably just view the information what we received. Personal computers, as we already know, personal computers are the general purpose computers for single user. So in such instances, most of the cases what we have is specific operating systems, most probably operating system, plus we have some hardware components. Those are not very strong, but those are much enough to do some work. For example, if we take, and that even big organizations use P3 machines, P3 machines kind of things for do lot of scientific work. But we have now i7, i9 machines, and we have much more processing power in those machines, so we can do a lot. But we are not doing it so well. So somehow that's kind of a thing that we need to understand. Personal computers, mostly like no need to worry a big amount of things. We know we need to focus on the specific scenarios, instances. We can use uh, personal softwares, and cost wise it's very cost effective, and some of features are not in there, but limited features are most enough for a person to use. Servers and enterprise systems, these are large computers, mainly servers. We can have different kinds of servers, application servers, database servers, and many kind of servers that we can find in real world. Supercomputers and grid computers, again high performance computers. Time back, those are the most powerful computing device that we can find, because thousands of millions of data processed in these grids and supercomputers. Again, nowadays we have much more stronger implementations than these grids and clouds, because cloud computing provides these resource or rich, I mean, cloud computing is a rich source for the resources. So we can expand our RAM storage or anything. Even we can install an operating system virtually, and we can get a work done. So basically these supercomputers and grid computers are quite powerful and very strong, very strong, to do many things, that's the most important point that you need to understand. but still we have grids and peer-to-peer and some of distance computing related stuff. Yeah, obviously yes. But main objective of those supercomputers and grid computers are mostly covered by the what we call cloud computing contexts. Okay. So there are some of examples that they are given here, with the forecasting, complex design simulations, and so on and so forth. So these are some of categories, but this is not the limited category. There might be some multiple branches and stuff we can find under this computer context. So basically, we have personal computers and server computers that we are using day to day life, that we are using. Next, the embedded computers. These are much more related to the IoT related stuff nowadays. So you need to understand embedded is mostly covered under this IoT, and super and grid computers mostly covered under this cloud computing. But still, we have personal computers and servers and enterprise systems. I think you can remember the general purpose computers designed to be used for a variety of applications, word processing, presenting, simulating, entertainment, and so on and so forth, based on general uh, purpose processor chips. These are just general computers that we can see, something that we do use day to day life. But nowadays we have much more expanded version than these general purpose computers, because we have portable devices, more towards portable devices. General computers like moving to the portable devices like mobile devices of, like, as an example, um, iPads or notebooks. Right? So these computers are moving for the mobility. Now probably everyone is using a laptop instead of a desktop. The reason behind is the mobility, and we can use these mobile devices in a variety of contexts than a specific static object, or an object that stays forever. Then we have embedded systems. What are these embedded systems? Basically, embedded systems are integrated into large device or system to perform specific function. Generally, use single chip integrated microcontroller devices. That's why I'm always telling these embedded systems are much towards to engineering, like electrical and electronic engineering contexts, because microcontroller programming, peak programming, all of these contexts are not that software engineers much focused on. Though we have a component for hardware, but we don't bother a lot. We mainly focus on some of piece of application of a software. It might be a web software, it might be a desktop or any other kind of a software. Somehow we focus on a software product than a hardware product. So embedded systems are mainly focused on these hardware components. Hence, most probably these contexts like embedded and IoT, even mostly embedded, is much towards now for software electrical engineers, not for the software engineers. General purpose computers use this specific purpose processor for subsystems. Example, graphics core processor, DMA controller, keyboards, and so on and so forth. Some of interesting things are here. Yes, obviously, because by handling all of these embedded systems, we are much familiar. If you take your mobile phone, sometimes they're giving updating software, updating operating system, or applying security patch or something. At that time, you haven't touched your mobile phone even. You haven't thought what happens behind the scene, what happens in almost. It takes everything, and it's doing very carefully everything that it requires to do, because all the instructions are stored in the specific hardware component. So it's much convenient and much easy. So almost everything is very clearly described, very clearly focused on these usage of all of these things under these embedded systems, because all the functionalities, the required functionalities are predefined. So uh, it's like nearly automated, so the end users do not want to focus, or a human do not want to focus a lot. Now, if we take this embedded system context, we have a number of examples in here. Microwaves, medical monitoring systems, video game controllers, industry controllers, and many other things. Right? So, large variety of devices we can find. But don't misunderstand, these are not mechanical devices. All right. So these are not mechanical devices. Instead of, these are electrical devices. Though these are just electrical devices, these focus on some of additional piece of software to take decisions. That's the difference in between an embedded device and an electric device or electronic device. Electronic devices, what happens? All the the power is flowed towards whatever the direction that the originally defined and how it flows. But once it comes to these embedded softwares, embedded systems, we have additional softwares. It's like a small piece of code, so small piece of sorry, small piece of software. This software is easily doing for us, almost everything doing for us. If there's an update, then it knows, okay, I need to update on these days. Fundamental components techniques the same, differences due to different design constraints. We have different design constraints now. These design constraints are much towards like reliability, robustness, and so forth. So these are quite powerful at that time. Embedded systems software interacts closely with hardware, that is usual. Interfacing, polling, interrupts, communication, and many other options are there. So, software operation based on the input, often designed as state machine. So, what happens in a state machine? States on, states off. It's like a switch off and switch off. As an example, if the switch is on, then the light or the bulb will gives the required rays for us, so we feel we are getting light. But the other components, whenever the switch are off, uh, everything is no nothing, everything is just keeping idle. So no power movement or any other thing, it's just keep it as it is. Hence we don't get any additional uh, lighting from this bulb or the light, whatever you are telling. State machines, kind of a state machine, just up and down, it goes, whether it goes up or no, whether the transaction happened or not. So all of these embedded systems like interact closely with the hardware. The system embedded systems are basically these focus on all of these structures. Some of embedded systems requirements. Embedded systems have different requirements to general purpose computers. Some of examples given in here: reduce system footprint. As an example, chip count and the size. There's a law called Molo. Now it's almost gone, but generally, the theory is explaining that the chips are increasing tremendously, right? And we have low power, resistance to electromagnetic noise. Now, time back, whenever there is an electromagnetic situation, there might be an electric pulse that we generate in the other way around to neutralize the entire process. But now it's much easy and much towards for automated resistance. So whenever there is an electromagnetic noise, that means if there are some additional power generated, now probably, I don't know whether you have this understanding or not. Think this is an electric path, right? So the electric path goes in this direction, and we can find nicely some of additional waves are generated. These are magnetic waves. So even we have some laws, right? That whenever power goes up, this is the direction that uh, what we call this magnetic is generated, basically. So that means we have much more magnetic power generated whenever there is an electric pulse movement. Whenever electric moves, it generates perpendicularly additional magnetic power. This power is known as electromagnetic noise. So the electromagnetic noise might be higher or lower based on the material, based on the input, based on the direction, based on the usage, and so on and so forth. Basically, these embedded systems is required to be much resistance to this electromagnetic noise, because if there is an electromagnetic noise uh, process towards like cross these two lines, it might be a big issue for these additional power can be generated in here, which makes additional effort that we need to focus on. So what we need to do is we need to understand to whenever we are designing, right, whenever we are focusing on this kind of a embedded system, it's mandatory to have a resistance to electromagnetic noise, robust. Basically, embedded systems should be really robust for different features like heat, vibration, shock, and many other things, because there is a possibility that embedded systems do have embedded to specified regions, specified focuses. Have you seen that a person jumping from the sky to land? 6 minutes or 8 minutes jumping from sky to land. No, you haven't heard. 2012 around, a person jumped from sky to land to earth. Sky in the sense, I think more than 3,300 feet, 11 kilometers or somewhere up. Then jump without anything. Then after a while, like the speed was around 1,000 kilometers per hour. The speed that because the velocity that the person is coming to the ground. So at that time only, there's a pressure meter. So what happens? That person realize that additional shockers are there. So there is an embedded system. It detects this because the person get rotated, right? The person got rotated because of this additional speed. So there's no option than that, because these are connected, so it's automatically get this. It's a specific additional uh, embedded system, so it's automatically pull up to the to secure. Then only that person got stable after a while. It's not a parachute. It's not a parachute. It's kind of a additional device. After a while, that person uses these parachutes and stuff to land. All of these are embedded devices. 2012, if I'm not mistaken. I can't remember extract. Yeah, it's around 2012. Far away, I think 11 kilometers or somewhere. I can't remember. It's from sky actually, using these all jackets and cover and everything. It's just jump without anything, right? And now some of what we call these MRI scanners and stuff. This. Scanning the brain and stuff to some like blood, what you call blood vessels are blocked. I can't remember the name. There are small pieces that blocking our blood vessels in brain. So these MRI scanners, they have automatically detecting all of these what we call these additional places that our vessels are not strong. Those are very thin and it's not strong enough to handle this low. The blood is not flowing at that time. There might be like something gone out and blood will spread it throughout. Then that's going to be last, right? So all of these MRI scanners are focusing on these kinds of, these are embedded devices. You can find lot of embedded components in these medical devices. One of reason is we do not want to configure a lot. If it is a software, it's basically having a lot of business requirements. Time to time, it's changing. Change this one, change that one, change the alignment, change the font color, change XYZ, lot of things. But when it comes to medical devices, it's like very limited. We don't want to. configure a lot. Like, have you seen this eye scanners? Eye scanners, you have to keep your head on that small piece of whatever, I don't know. Then we have to keep our eyes. Then there's an image, so we have to look into that image, right? So they don't have to do lot of functionalities. All they do are doing is they want to calculate the what we call this f value, the focal value of this glass, our lenses, and whether is it perfectly working, and so on and so forth. The configurations are minimal. They don't want to configure a lot, they don't want to change a lot. They want to focus on a specific feature. So the embedded systems are the best in that case. So that's the point, that these things, in that point, that the variations are limited and the functionalities are very common. And in the other hand, we have to focus on additional resistances, especially the vibrations and shock. It's obvious. Okay, so a person jumping from the sky, what happens? We don't know what happens. There's the first person who jumped from the sky. And no idea what happens. No protocol to understand what happens. Sometimes that person might, this last jump might happen, but that person safely landed, right? Because of these techniques. And generally do not need very high processing power, because if it takes a couple of seconds, it's not a big deal. We can manage. Think your medical devices, keeping your eyes, you can wait couple of minutes even, right? Even few seconds is delaying, it's not a big deal. So it's totally okay. But think internet, 5 seconds no internet, Facebook is not scrolling, 5 seconds you're getting upset. 5 seconds it's not scrolling, what the hell is this? I said 5 seconds you can't stay. You're getting upset because at that time we want high processing power, very high processing power. That's why all these YouTube, Facebook, and all social media platforms keep the people entertaining continuous internet. Like they keep buffer. If you have some experience, that YouTube, they keep some additional buffer always. You can see there's a red line front. There's a additional gray, dark gray line, additional buffer, additional data taken into the video to keep. If there's a small delay of 2 to 3 seconds, it can handle. The end user will happy. End user can't understand 5 minutes internet loss and comes back. At that time, still it's playing very well. At that time, we want high end processing power. But once it comes to these embedded systems, we don't want to have this kind of complex situations. In some cases we want real-time responses, more towards like aircrafting and space stuff. So all of these things required to communicate real time. If something gone wrong, they need to update on time. So that's the point of these real-time responses. Use microcontroller chips to integrate memory and I/O interfaces, circuitries, system on chips. So a lot of components that we have that integrated, and these components do have a small portions of memories, small portions of interfacing, and circuitries, and many other things. Right? So that's basically the entire story that you need to understand how it should work and how it works, and so on and so forth. Right? Any questions up to now? No? Some of additional information is given for you, but I don't think so you want to bother a lot. So this is the main processor. This is a typical microcontroller with a SoC structure. Probably these are big towards electrical and electronic engineers, but having this kind of knowledge will be valuable. But I don't think so it's mandatory to work as a software engineer. So we have different components like memory, processor, converter, analog to digital converter, and different serial interfaces. So basically these are interfaces, and many other structures are there to communicate, right? So some of additional components like timers, counters, many other things are there. Once it comes to these microcontrollers, we say SoC, we have much varieties of SoC structures are there. On the other hand, to maintain I don't recommend you to go through if you are not really interested to work with this electrical engineering. If you are focusing on software engineering, it's great that you can go through just software work, not much towards to this. Some of system behavior is given here. Transformational systems have all inputs ready when involved. The outputs are produced after a certain computational period. As an example, you can see this diagram that it's clearly representing three different levels of data and different kinds of inputs, processing, and outputs are there. Right? Inputs, processing, and outputs are there. Finally, we have results. So this is the standard structure. Data converts into a result and information at the end of the day. Somehow we have input, processing, and output cycle. Apart from that, some of additional information here. So all of these information systems are focused on this transactional mechanism. That's why they are telling transformational systems. A data input is taken and it returns an output. Then the order of data inputs is and execution must be in, yeah, that's fine. So some of information here, basically it's just input, processing, and output with two other ends of the data and information. Some of places you can find instead of result information in here, it's totally okay. Then an interesting topic is reactive systems. Now, this is the standard structure, standard systems that you have seen in many places basically. But when it comes to reactive systems, these are very powerful because it adjusts its behavior based on the external environment. As an example, the system continually interacts with the environment, receiving similarity and producing outputs in response. Order of events in a system is not predictable, determined by external events. The execution of reactive systems does not have to end. Now, this is like continuously checking whether what kind of an environment is in here. For an example, basically, a bad example, think we have to monitor weather. This is the place that monitoring the weather. So what we need to do is we need to communicate with this kind of a reactive system. What happens here? The reactive system always getting inputs from the external environment. Further, we it gives some of outputs to the external environment. Usually the external environment in this case it might go for environment, or else like internal state might change in the dashboard or the structure, whatever the structure that you are using for the communication. So it's a recurrent, or basically it's continuous work. It takes all of these things and transmit and perform the transactions continuously. So it focuses on all of these things very well. Typical of embedded systems, environments applications, commonly designed as finite state machines. Basically, these are finite state machines. But state machines, finite state machines, those are some of computational machines that you can learn. Well, I don't think so you want to go through in detail, but having general understanding is mandatory. Hence we have given some of general discussion. But if you are really interested, you can go through for detailed you want. But my general suggestion is having an overview or basic overview of what are these reactive systems, what are these proactive systems, how the systems are behave, and so on and so forth is more than enough for your understanding. Next one is system states. A system can only exist in a defined state when it is waiting for some in the external environment to occur, or it is waiting for current activity in environment to change. Basically, what happens in these places we have to focus on an interaction. right? So basically, an interaction of uh, that is observation of like how the environments are changing, right? Right. Jama. These are basically perform different states. Sometimes it might be an input state to processing state, some of processing to input state or any other thing. More specific situation can be discussed in these state machines. I think you have drawn state chart diagrams, system analysis and design, state chart diagrams. No, no, I haven't heard even that word. Heard. I heard that word. Good. I can't remember what is that. Can't remember. Can. Good. Huh? A level computer. In here, no, they haven't teach us bad fellows. You- no, I haven't heard even. This is the first time. System analysis and design. Huh? I, I don't know what the hell is this. Good. Right. Basically, it represents, this is a sample of state diagram that we have discussed, where it stops and which switch on and switch off, basically running temporary error from the sensor and structure. Some of the things are here, but you don't want to bother a lot. I will discuss very high level situation in here. Whenever the switch on, initially it was stop. Think a switch like this, a switch like this, switch is off, it is in stop stage. So you switch on, it comes to a running stage, which switch on, this gives the power for this place. Then after a while I'm switch off this one, then this device is not working furthermore. It runs throughout. This is the normal situation, like nearly 99.9999 whatever value. It's this is the normal situation that continuous transformation happens. But rarely we can see these kind of things. Some of error in here. The switch is not working. Switch on, switch off, switch on, switch off, but it's not working. There might be some internal wire is disconnected. Wire is disconnected. So or else this device is not receiving the relevant signals, right? So these kinds of things can be happen. So stop running, running to stop, running to stop, and structure is happening later on, or somewhere we don't know, there might be an error can be occurred. So this error handling situation is very powerful in these instances. Clear? Very sleepy. No, it's very sleepy discussion. Trans- Transitions, a valid state change is called transition. A transition connects relevant pairs of states, fixed number of events usually. Each event can have associated with actions. Each event can have transition. So these are different kinds of events: running, stopped, and error. These are transitions, switch on and switch off, error and stuff. State diagrams, visual representation, a directed graph. You know, when it comes to graphs, we have a number of types of graphs. One is a directed graph. Sometimes you can find undirected graphs and stuff. Basically, it's directed graphs. State as nodes. These are nodes, and transition as its. These are the its. Right. So that's the whole story. Now, a system typically has rules governing by its behavior. These rules can specify system change from one state to another state, right? So this is the whole story that you need to understand in this context. Any questions? All good? Very nice. Embedded systems. What are these embedded systems? Real-time systems, standalone systems, network systems, mobile systems, and many other types of systems are there. So we can classify all of these things based on different criteria. So based on a one criteria, this slide represents four different stages: real time, standalone, then networked, and mobile. So we'll see what happens in next layers. Real time responses. What happens in a real time response, guys? As I told, whenever a situation or an instance occurred earliest as possible, near zero, right? Near zero, the information is transformed to the other end. Near zero, it transforms to the other end. That's the whole story of this real-time embedded systems. Actually, these what we call aircraft engineer, they have to focus on near real-time embedded systems because they want to communicate earliest as possible. If there's a delay, it might be a big problem. Similarly, whenever there is like space shuttles and many other places, we can find the same thing in here as real-time responses. uh, some of diagram is given in here, where it happens, and so on and so forth. Real-time operating systems, another type of operating system we have discussed operating systems in detail, very detailed explanation. Take a pen and paper and draw operating system state chart diagram. State chart diagram.